Okay, welcome back. So let's take a look now at modules. A module is simply a file whose name ends in .py, and it contains some arbitrary Python code. You can pull a module into a text editor, and from within the text editor run the module, and that will just execute all of the code in there. In fact, that's exactly what I did here with userage. Userage.py is a module, and I have loaded this module of code into my editor, my idle editor, and from within idle I can say run module, and it runs. So this module, userage, contains a program that just starts running when you say run, and does whatever it does. But it's also common to have modules that are not themselves programs, but instead just contain a whole bunch of function definitions, or class definitions, or definitions of constant values, so that you can do what's called importing those modules into other code to make use of the facilities that those modules provide. All right, so when you say import math as m, you're importing a module of Python code that just contains a whole bunch of definitions of things and does not have any part that just automatically starts executing. Does that make sense? Sort of? All right. So the shell, even, in some sense, is a module, and the shell thinks of itself as being the main module. Okay, well, I already mentioned, you can have variables defined, functions, classes, this kind of stuff. And there's a very simple rule for taking the name of the module file and figuring out what the module name is that you have to import. You just chop off the .py extension, and that's the module name that you have to import. So when you say import banana, Python is going to look on your disk for a file whose name is banana.py, and it's going to pull that file in. Okay? Within the current module, sorry, I didn't say that right. Within any module, the special variable __name __ contains the name of the module. So if I'm in the shell and I say print __name __, this is going to print the module name of the interactive shell. The interactive shell always believes that it's the main module, so what gets printed out is the string __main __. Okay? But every module has this underscore. What are these called? Yeah. I just encountered the official Pythonic name for these kinds of variables because they all start and end with double underscores. So they're called Dunder variables. Double underscore variables, Dunder variables. So I'll just call this Dunder name from now on. And the value is Dunder main. All right. There's a function vars that will show you all of the current variables that your current module knows about. Now, in this case, I'm typing it interactively to the shell. So this is requesting the variables that my shell currently knows about. And you'll notice that the variables are represented as a dictionary. And within the dictionary, the first part, the key, is the name that the variable has, and the second part is the value that the variable has. So in addition to the Dunder name variable, we have Dunder doc and Dunder package, Dunder file is the name of the file that is currently open, which is this huge user age thing. And then I've got my age bad variable, which is false, my age, which is 23, and so on. Okay, so let's see now how we can create a module of functions and make use of this underscore, this Dunder name variable. I haven't practiced saying Dunder enough. It sounds stupid to me. But we'll see how to make use of this variable to figure out, which module you're currently in. So let's suppose that we have a module in a file called module.py. In here, I have a function defined called fun1. I also have a constant value defined, cnum, which is our course number represented as a string. And I can test whether this module is the current module that I'm executing by comparing the variable name Dunder name to underscore underscore main underscore underscore. If the current if the value of Dunder name is equal to Dunder main, that means that this is the current module that I'm executing, and it's common in such a case to have some testing code that tests the functions that have been defined in the module and that displays or does something useful with the variables that have been defined within the module. So this is a very common line of code. Whoops. This is a very common line of code that you're going to see in lots of modules, and you're going to start using this yourself when you define your own modules. Okay. So if this module, this mythical module whose name is my module, is the module that I have loaded into my editor and I'm running, that means that it's the current module. It's the main module, and the code underneath the if there will be executed. But if instead of directly loading the my module into my editor, I instead have some other program loaded into my editor, and that program has an import statement. All right, so this program that I have loaded into my editor says import my module. Well, now a copy of my module gets pulled in where the import statement is done. But now that module is not the main module. It's a subsidiary module of the current module that I'm editing. And its name will be my module. Okay, so the test will fail, and I will not do whatever code is underneath that if under name, Dunder name is main. All right. I'm reasonably confident that maybe 2% of you had any idea what I was saying there. So let's look at an example which will hopefully clarify what in the heck I'm talking about. So here is a module named MyMath. And this module defines three functions. A square root function, a cube function, and a MySum function, which do the obvious things. That's the top part of the module. Now the bottom part of the module contains this if-else decision. This is the same file, it's just the bottom part of that file. So if I am directly working on mymath.py and I run mymath.py, the value of the underscore name variable will be main, and I'm then going to execute these four print statements to test the components of the module. But on the other hand, if I have imported my main into some other program, when I get to this point in my math, the name will be my math rather than underscore main. And I'll drop down here to the else part, and I'll just say, oh, this module has been imported by some other module. It's not the main module itself. Come on. Okay, so let me pull in this file. And I think I made the same mistake here of not already loading that in. Oh, there we go. Okay, so I need from files to pull down mymath.py and myprog.py. And I'll copy these guys into my correct directory. That's not a correct directory. There we go. Okay, so now I have these files in the directory where my editor is expecting files to be. And let me open mymath. This is the file that we just looked at. It contains these three function definitions, square root, cube, and mysum. And then in the bottom half, it contains this if dunder name is equal to main, do some tests of the three functions. Otherwise, just report that, oh, this module must have been imported by some other module. All right, so I'm going to run this now by pressing F5. And, okay, the file gets loaded in. The function, square root, cube, and mysum all get defined. And then, because this is the current module that I'm editing, it is therefore the main module, this test is true, and these four print statements are executed, telling me that the module name is main, the square root of 3 is, and this is going to call the square root function with 3 as the argument, and that looks correct. 12 cubed is 1728. I assume that's correct. I can't do that one in my head. 144, 1. All right, 1440 plus 288 is 1728. Yes, it is. All right, and then the sum of these 6 values is whatever it is, and I'm using my args, my star args variadic positional parameter to receive those values. Okay, so let me say that quickly one more time. This is the file that I'm editing. This is the file that I'm currently working on. When I run this file, it is the main module. When I run this file, the three function definitions are defined, and the special variable name underscore underscore is main. It is the main module, and those 4 print statements are executed. Does that make sense? Yes.
We will need to know that the main module has SQR, EQ, etc. We can't access those without knowing it before.
Well, it's all one file. So here, this is the one file that I'm currently editing. Presumably, I, who have created these function definitions, know what they're named and know how they work.
So say I had to use that.
Okay.
I create it. How would I know that? Sure, we can list it, right? Sure. We can list those functions within the module. So
Yeah. When you import this module, you'll be able to see that these functions have been defined. And something that we have not done here that we should do is to create documentation for these functions. You can. I'm slightly jumping ahead here, but you can create what are called doc strings, saying square root of x computes the square root of x. Okay, and if let me run this now. A doc string is just a string between the def line and the beginning of the definition of the function statements. I'm going to save this and run it. It runs. And if I now want to run square root manually, when I hit the parenthesis, I see the doc string. So this typically is a feature of whatever development environment you're using. In idle, it just shows me the doc string that's part of the function definition. Good. Any other questions? Okay. All right, so this is what happened when I was working directly on MyMath. MyMath is the program I'm modifying. MyMath is the program I'm testing. When I run it, it is the main module, and so all of these print statements here are executed. Now, let's look at another program, though. This is myprog, separate file, myprog.py, and in this file I'm importing MyMath using the abbreviation So the only statement in myprog is this variable definition where I'm saying x gets 123, or x refers to 123. And if this program is the main module, then I will invoke these, then I will invoke these print statements down here, and notice that I'm calling mm.cube and mm.square root. So I'm using, in this program, I'm using functions from the other module, from the MyMath module. Okay? So let me run this one now. Let me load this guy in. So this is myprog. All right, now in my integrated development environment, I am currently working on the myprog.py file. So when I run this file, it will be the main module. The first thing it's going to do is to import MyMath. Well, let's take a look at what happens in MyMath when MyMath is not the main module. Well, when MyMath is not the main module, what happens is that these functions do get defined, the function definitions do occur, but name is not equal to main. Okay, because MyMath now is not the main module, it is a subsidiary module that's being imported. And so we're going to drop down here and do the else part, saying imported module name is, and we'll discover that the value of Dunder name here is MyMath rather than __ main. All right, so I'm in myprog now. MyProg is my main module. I'm going to run it by pressing F5, and the first thing the program does is to import MyMath as And this statement here is the last print statement from within MyMath, saying imported module name is MyMath. Then the three statements in myprog, the three print statements in myprog are executed, saying module name is main, x cubed is whatever the cube of 123 is, and the square root of 123 is whatever the square root of 123 is. This one I definitely can't do in my head. neither of these, but we'll assume that they're the correct values. So did you see what was going on there? I have a program that's importing a separate module. And when it imports that module, it imports it with its file name with the .py chopped off as the module name. So in some sense, Python is strange compared with languages like C, C++, Java. In a C or C++ program, everything gets kicked off by a function whose name is main. I don't know if you've done C or C++ ever. Where does the program kick off when you do a Java program? I've forgotten. I used to know. I'm sorry? Oh, right. Okay, so Java is actually, can be a little bit Pythonish, right? Okay, well, I don't think I want to go down a rabbit hole that maybe isn't really helping. But in Python, any module can be the main module that you're currently editing and that you're currently executing. And you can have, one module import another module, and that module import the, yet another module, and so forth. And they're all imported as subsidiary modules, with their names being set to whatever the file name is with the .py chopped off. Okay. Now, it's possible to get very sophisticated as far as organizing the structure of modules. But for our purposes, all we need to know how to do is store all of the files in your program in the same directory, so that when you open one of them and you run it and it imports another one, it will be, Python will know automatically, oh, that file is in the same directory that I'm currently in. And you don't have to worry about path names and environment variables and stuff like that. All right, well, now we're going to totally switch gears and take a look at a very important module called Numpy, which allows you to create n-dimensional arrays. The data type of these is ND array. Numpy is just one of several specialized modules for doing things like matrix algebra, statistical analysis, plotting, machine learning kinds of algorithms, and so on. And most of these very well-known modules have common abbreviations that are used. So for NumPy, the most common abbreviation is NP. And often if you pick up a Python book that's using NumPy and you start flipping through the examples, they'll just use NP and assume that you understand that that means NumPy. Or they'll use PD and assume that you understand that that means pandas, and so on. So we, in the rest of this lecture, are just going to use NumPy with the abbreviation NP. Okay. So roughly speaking, an ND array is sort of like a list with a couple of very important distinctions. First of all, the ND array items are guaranteed to be stored in consecutive contiguous memory locations on the machine. This turns out to make ND arrays much more efficient to access than ordinary lists. Also, the entire NumPy package is actually written in the C language, and it's optimized for vector-oriented computations. Okay, so it's really fast for doing matrix kinds of computations. You can build, sorry, yes?
Does the ordinary list then have like an object and then a pointer to the next object?
Yeah, an ordinary list, it's I'm not sure. Oh, I have a whiteboard. Oh my goodness. I'm not used to actually writing. Oh. Anybody see a pen hanging around here? No. Okay. Okay, so I will do hand waving instead. So a list in Python, if you create a list with values 1, 3, 5, 9, let's say, you don't have like an array containing a 1 and a 3 and a 5 and a 9. What you have is a sequence of locations with a reference to a 1 and a reference to a 3 and a reference to a 5 and a reference to a 9. And the 1, the 3, the 5, the 9 are stored in a separate area of memory, and the list is an object that has internally what are called pointers to those things. So it's a really convenient way of organizing data from a user's point of view. Everything looks nice and tidy and clean. From an execution efficiency point of view, it's just a crazy way to do business. Because you can't access anything directly. Everything that you're accessing is done indirectly through some kind of pointer. And if you have a list of lists, like earlier I created M2, let's see, M2, no, oh, each time you run a program, your shell forgets everything that it used to know. So all of those lists and things that I created earlier in the class are now gone. So let me just build one here. M2 gets a list of 1, 4, 5, 9, 1, 9. All right, so M2 is now a list of lists. But what that really means is that M2 is a reference which refers to a list which is stored somewhere, and what that list actually contains is 3 references to 3 lists that are referring to a 1 and a 4 and a 5 and a 9 and the same 1 and the same 9. You know, so you've got all these indirection operations going on internally in your program from just writing this simple looking thing. So yeah, direct Python is, you know, like, I don't know, order of magnitude like 10 times slower than something like C or Java. But the trade-off is that people can write Python code a lot faster and get stuff working. So, you know, so if you need to get something working fast, Python is a good language to use. Other questions, comments? Okay. Okay, so we know that we can create a list by using range as an iterable with our list conversion function. Analogous to that, if I say import numpy as np, now numpy is a pretty big module, and my laptop is a little clunky, so notice how long it takes to pull that thing in. There we go. Now if I say np.arange, meaning array range with 10. Whoops, I forgot my equal sign. This creates an ND array containing the 10 values 0 through 9, but guaranteed to be stored in contiguous consecutive memory locations for higher efficiency. Okay, so A1 is an ND array rather than a list. And if I say type A1, I'll get told that A1 is an ND array. ND array for an n-dimensional array. Although this happens to be a one-dimensional array. You can subscript into an ND array using the same kind of indexes that you can use for lists. So you can use both positive indexes to go forward or negative indexes to count backward from the end. All right, here's my A1. If I say A1 sub minus 2, that's going to be the 8. It's the second to last item in my ND array. Or A1 sub 2. Actually, that's the third item in my ND array, because indexing forward starts from 0. Now, it appears that my ND array is containing the same kind of integers that I might have in a list, but actually the integers that I'm storing in my ND array are restricted to 32 bits wide. And again, this is for efficient memory access, because this is the size of integers that or this is one of the sizes of integers that modern computer processors handle extremely efficiently. So these are what are called 32-bit integers, which are similar to the int data type that you would find in C or C++ or Java. And if you ask for the type of an item within A1, you will see that this is a Numpy int32, not a Python int. The range of values that will fit into an int32 is roughly between plus or minus 2 billion. But if you try to go much beyond 2 billion or much below negative 2 billion, the value will not fit. So if I say A1 sub 0 gets 1 through 4, 1 through 4, 1 through 4, 1 through 4, that's going to be too big, and I get yelled at that that's too large. An ND array is iterable, so you can easily convert an ND array into a list or a tuple or a set within Python. You can loop through the items in an ND array using a for loop. A range behaves like the range function. But more generally, you can create an ND array from any iterable object in Python by using the np.array construction function. So if I say A2 gets np.array, and then I give a list of integer values, let's say 1, 3, 7, 8, 12, I will get an ND array containing those values, assuming those values are small enough to fit in 32 bits. Okay? Likewise, if I say A2, here I'm using array with a tuple of floats, and that also works. A3 gets np.array, and I'm using a tuple of 718, 3.14. So now I'm using a tuple of floats as my iterable. This also creates an ND array. However, these are not. What did I do? I must have pressed my window button. Go away. Go away. Go away. There we go. These things are not quite the same as Python's float. If I ask for the type of A3 sub 0, I get told that this is a float 64. All right, so it's a 64-bit wide floating point number. All right, now on this particular system, in this particular version of Python, NumPy's float64 data type and Python's float data type are exactly interchangeable, because Python's float data type is also a 64-bit floating point. So in this environment, NumPy's float64s and Python's floats are exactly the same, whereas the int32 and the int are quite different from each other. Another very important difference between lists and tuples and sets versus ND array is that although lists and tuples and sets can contain different types of values, all of the values in an ND array have to be the same data type. And some nasty conversion called upcasting is used if you try to create an ND array in which the values you give are of mixed data types. So here I'm saying A4 gets np.array. I'm providing a list containing an int, a float, another int, another float, and NumPy is not going to tolerate having mixed integers and floats in the same ND array. So what it does is it figures out, well, which of these two data types is simpler, and ints are simpler than floats, so it upcasts the ints to be floats. And consequently, everything in the ND array is a float64. And you can see that where I type 3 in my list to create the array, the ND array, it's actually stored in the ND array as 3.0. And likewise, 7 is stored as 7.0. Okay, now, so indexing of lists versus ND arrays is similar, but operations like multiplication, addition are completely different. For a list, remember that multiplication actually is interpreted as a concatenation of lists. So if you say one list times... No. I was thinking of this example down here. So addition is interpreted as concatenation. This should say repetition up here. So when I say ls1 times gets 2, what I get in ls1 is a repetition of the original ls1 twice. Sorry for that typo there. So let me say ls1 gets list range 5, ls1. And if I say ls1 times 2, we know that that's going to give us a list that's repeating that same thing twice. If I say ls1 plus ls1, this does concatenation. And if I try to say something like ls1 plus gets a 5, like this, well, that's just not defined. I may want this to append a 5 to my list, but that doesn't work. I just get yelled at. To append that value 5 to my list, I could say ls1 plus gets the list containing 5, because that's the same thing as saying ls1 gets ls1 plus 5. And here we're doing a concatenation of one list to another, and then we're just redefining ls1 to refer to that new list. Make sense? Okay, but ND arrays are doing vector arithmetic. They're not doing concatenation, they're not doing repetition. So when I use these operations with ND arrays, multiplying by 2 actually multiplies every item in the ND array by 2. So here's my ND array A1, and if I say A1 times gets 2, that's fine. I'm multiplying a vector times a scalar, and I get the vector modified so that every item is now multiplied by 2. If I say A1 plus A1, instead of doing concatenation, this actually computes a sum of the two vectors. Now, I'm not modifying A1 here. I'm just taking a copy of A1 and adding another copy of A1, and I get, as my result, my return value, if we will, I get an ND array, which is the sum of these two things. All right, but A1 itself hasn't been changed by that. If I had said A1 plus gets A1, that would actually change A1 to itself plus itself again. Scalar addition is fine, and what happens here is that every item in the array simply has that scalar value added to it. All right, so whereas I started out here with even numbers, 0, 2, 4, 6, 8, if I add 1 to every item, I'm going to get a sequence of odd numbers instead as the contents of A1. Good? Okay. Let's see. Now, we can slice ND arrays. We talked about slicing lists. We can slice any kind of so-called sequence. So we can slice a string, we can slice a list, we can slice a tuple. We can't slice a set because there's no concept of order in the values in a set. But we can slice an ND array. And here, all right, I'm saying A2 gets np.a range 10. If I say A2 you would tell me if we haven't talked about slices, wouldn't you? We have talked about slices, haven't we? Good. All right, so A2 sub 2 colon 5. That gives me a slice from the sub 2 item up to but not including the sub 5 item. So that gives me a slice of the 2, 3, 4 from A2. Okay? Now, unlike lists, where when you ask for a slice, what you get back is a new copy of a list that's just that slice from the original list, in ND arrays, what you're getting is a view on the underlying ND array, not a separate copy of a slice. So when I say A2 sub 2 colon 5 gets minus 8, all right, I'm doing a scalar assignment here. That's going to actually modify the underlying ND array A2 to contain minus 8 instead of 2, 3, 4 for the items in that slice/slash view. So here again is a very important difference between how lists behave versus how ND arrays behave. When you ask for a slice, you're really just getting a view on a subpart of the underlying ND array. If you want to get a separate copy, either of an entire ND array or of just a slice of the ND array, you have to use the copy method. All right, so here's A2. If I say A2 sub, let's say 7 colon, all right, so that means A2 sub 7 all the way to the end. Now, as I've written it there, A2 sub 7 colon, that's just a view, but what I want is an entire copy of that thing, and I'm going to call this A3. All right, so A3 now contains 7, 8, 9, but it's a completely independent copy of 7, 8, 9. It's no longer a view on A2. So if I say A3 gets 7, that's valid. Actually, I think I just made a mistake there. Right, I did. Do you see the mistake that I made? I was trying to set all the values in A3 to 7, but what I actually did was I changed the reference A3 to refer to the value 7. So I didn't change my ND array. I lost my ND array. I've lost track of my ND array. So I'd better, all right, so A3 now just refers to the integer value 7. That's not what I wanted. So let me get my copy of that slice back. What I wanted to do was to say A3 colon, A3 subcolon gets 7. Okay, so if I just use a colon here, that means the entire ND array. I'm getting a slice consisting of the entire ND array, and that means that every item in that ND array A3 is going to be set to 7. And that works fine. A3 now contains 7s, but A2 is completely unaffected. A2 does not contain 7s out here because of the copy. Good? Aren't you glad that this class is 3 hours long? I hope you're glad that I'm recording it all. All right, so we've looked at one-dimensional arrays. Now we're going to take a look at multi-dimensional arrays, and specifically two-dimensional arrays here. So I can also use the array construction function and pass it a two-dimensional. In this case, I'm passing it a list of lists to create the array from. And this will create a two-dimensional ND array. So A1 gets np.array. And I don't remember what those numbers were, but, well, let me look them up. All right, so, 1, 2, 3, 4, 6, 4, 2, 0. That's easy to remember. 1, 2, 3, 4, comma, 6, 4, 2, 0. Okay, so I've got a list of lists here, and that's going to build for me a two-dimensional ND array with 2 rows of 4 columns each. And in fact, I can ask with the ndim attribute what the dimension of the array is. So A1 is a two-dimensional array. And I can also ask what the shape is. And the shape is going to be a tuple telling me how many rows and columns this array has. Okay, so there are 2 dimensions to this ND array A1. And the shape is 2 rows, 4 columns. A one-dimensional array, like I'm creating here, in fact, I already have a one-dimensional array sitting around, A2. A2 is already a one-dimensional array. I can ask A2's ndim, and I get told 1. If I ask A2's shape, well, the shape is already, the shape is always a tuple. So remember that if you have a tuple only containing one value, you have this silly extra notation of the comma before the closing parenthesis. So that tells me that this is a one-dimensional array containing 10 columns. Or it's a vector of 10 items. I can use reshape not to modify the array directly, but instead to get a copy of the array reshaped into some different shape. So let me do as is shown on slide 49 here and create A2 as an array of 12 items, 12 values, so that I can say A3 gets A2.reshape, and I could do that as 3 rows of 4 columns, or I could do that as 4 rows of 3 columns, or 2 rows of 6 columns, or 6 rows of 2 columns. I can take those 12 items and reshape them into anything that gives me a total of 12 items. All right, so A3 now has 3 rows and 4 columns. And A3 shape is obviously 3 by 4. Okay. There are certain kinds of two-dimensional arrays that you can create easily just by calling different construction methods. For example, if you want an ND array of all ones, you can specify a shape tuple as an argument to the np.ones function. Now, this has to be a tuple, so I'm going to say 2 by 4. Okay, so I'm going to get an array of ones with 2 rows and 4 columns. Whereas if I said 2 comma 4 without making a tuple out of that, this is going to be an error. All right, so this seems a little squirrely, but you do have to remember that when you specify a shape to one of these construction functions, it's got to be a tuple. It can't just be separate arguments. Likewise, I can create an array of zeros. I can create an array of any arbitrary value by using this full creation function. And I can create an identity matrix in either of 2 ways, by using the I function, EYE, or the identity function. They both do the same thing. Now, I find this a little odd that they don't just use capital I as the name of an identity matrix, but you know, because you can use uppercase letters for function names. But the upshot is that both np.I of 4 and np.identity of 4 give me the same thing.
Are there functions to make upper triangular and lower triangular?
You can do that using a comprehension. Let's do that. I'm sorry?
So you can just subtract it.
Yeah. Okay, now here is a 3 by 5 array. Okay, and I'm definitely going to cheat building this thing. So here's what I'm going to do. I'm going to say A1 gets np.array, and I'm going to create a list of lists, and I'm going to use comprehensions here. So I for I in range oh, these are even numbers. So all right, so I'm going range 5 times 2. Okay, so there's my first list. It's going to be even numbers from 0 to 8. My second list is going to be odd numbers, I times 2 plus 1, for I in range 5. That's my second list. And what does my third list look like? Negative numbers. So this is going to be I for I in range starting from -5, going up to but not including 0 with a step size of 1. And okay, so I'm creating my ND array of 3 rows of 5 columns using a comprehension for each of the rows. And so there's my A1. Now in the end, I probably did more typing there than if I had just manually typed in these values. However, since I make lots of typing mistakes, and it's easier for me to think about for loops than it is to think about, you know, value, comma, value, comma, value, comma, value, I probably made fewer mistakes defining the array this way. Alrighty. Now, we looked at the idea of slices in one-dimensional arrays. So here's my one-dimensional array A4, and I can say A4 sub colon 3, which means from sub 0 up to but not including sub 3, so that's going to be just the 0, 1, 2 part here. But what if you have a two-dimensional array? Then how do you get slices from a two-dimensional array? Well, it turns out that you can use slice notation to specify which rows you want, and also use slice notation to specify which columns you want. Okay, so here I'm saying, give me all the rows from row sub 1 to the end, and give me all the columns from column sub 0 up to but not including 3. All right, so that's going to give me this row and this row, the sub 1 row and the sub 2 row, and the columns are going to be 0, 1, 2, but not 3. So what I'm going to get is a slice, which remember is a view on the lower left part of that two-dimensional ND array. Okay, so A1 is this thing, and if I don't want documentation. I know what I'm doing. A1 sub what that was, 1 colon, I think? Yeah. A1 sub 1 colon, so I'm getting rows from 1 to the end, and then I want columns from 0 up to but not including the third column. And that allows me to get just a corner of this two-dimensional array. Since that thing is a view, if I say A1 sub 1 colon comma colon 3, let's say times gets minus 1, that will actually change the sign of all of these 6 values in the lower left part. Okay, so I used to have negative values here and positive values there, but now now the signs have all been reversed by my multiplication on that view. Okay? Okay, now if I have a two-dimensional array with rows and columns, and I just use one subscript, what I get is that particular row. So A1 is 3 rows and 5 columns. A1 sub 2 is just the last row. Whoops. Sorry. And it is a row. So A1 dot ndim is two-dimensional. A1 dot shape is 3 by 5. A1 sub 2 dot ndim is 1. A1 sub 2 dot shape is going to be a tuple containing just the value 5 and a comma. Okay, because this row is a vector of 5 items. All right? Okay, I can get all columns by specifying colon as my second index. I can get all rows specifying colon as my first index. I'm trying not to keep you here forever. Here we go. So all columns, I'm sorry, all rows, but only the first 2 columns. Let's do that one. So A1 is 3 by 5. A1 sub all rows, but only the first 2 columns. Now, colon 2 means the sub-0 column and the sub-1 column. So I'm going to get this part of the first row, the first two from the second row, and the first two from the third row. So I'm basically just getting the left two columns of this array. And if you step through these various other examples, I think it will, you'll see what's going on. I think it will make sense to you, okay? Slicing is just one way of stepping through or of accessing items within an ND array. And it's fine if you want to access certain rows or certain columns or certain subsections of your ND array. But sometimes you need to be able to index within your array more flexibly. Like you might want to be able to say, okay, identify for me everything in the ND array that is greater than 10. Or identify everything in the ND array that is close to 0. Or identify everything in the ND array that is even. You might want to do those kinds of requests. And that involves using what are called Boolean indexes instead of slices. So, my first example here's my A1 array. And in my first example, I'm creating a Boolean index called B rows, which contains true, false, true. Yeah, I meant to say equals. B rows gets true, false, true. Is that right? Okay, I know that looks like browse, but I promise it's B rows. It's Boolean index for rows. And if I say A1 sub B rows, these indexes here, these Booleans here, are going to be used to indicate whether I do or don't want a certain row in my result. So what I'm doing here is I'm picking row 1, not selecting, I'm selecting row 0, not selecting row 1, and am selecting row 2. So the first row and the last row are all I'm going to get out by using that Boolean index. All right, now that's something that I can't do with slices. With slices, I can only get like rectangles. I can't get first and last or middle and fourth or things like that. So Boolean indexes allow me this flexibility now to do that. I can also do Boolean indexes on columns instead of rows by using the slice notation to select all the rows, and then a Boolean index. Here I'm just giving a literal I'm just giving a literal list as my Boolean index, indicating that, okay, I want all the rows, but I only want column 0 and column 3. I don't want columns 1, 2, or 4. And so that's how you would select just certain columns from the two-dimensional array instead of blocks of contiguous columns. I can also do comparisons, relational, equality, logical comparisons. So if I have this array A1 and I do the comparison A1 less than 5, what I get back is a Boolean index which is true everywhere that the value in the array is less than 5, and false everywhere that it's not less than 5. Okay, so 6 is not less than 5, 8 is not less than 5, 7 and 9 are not less than 5, 5 is not less than 5, and so all of those values that are greater than 5 are false. Now, what's that any good for? Well, I can now say something like A1 sub a less than 5. All right, so now I'm using a Boolean index on the entire array, not just on certain rows or certain columns. I'm using a Boolean index on the entire array, and I'm saying if a is less than 5, change it to, let's say, 0. And I need to say a1 less than 5, not a less than 5, equals 0. Okay, so now I've modified my array so that all of the values that were less than 5 have been set to 0, and the only values I have remaining to analyze are the ones that are 5 or greater. So you can think of this as being like, you've got this bunch of data and you don't want to deal with the small outlying data, so you can identify that small outlying data and just arbitrarily clip it down to 0. Okay. These Boolean comparisons can get to be fairly complicated, and for reasons that I don't think are any good, you can't use the words and, or, and not to create logical combinations of things. You're required to use the symbols ampersand to mean and, vertical bar to mean or, tilde to mean not. It inverts. It converts trues to falses and falses to trues. We also have another symbol, the caret symbol, or the hat, or the circumflex, many different names for that guy, which gives you an exclusive or of the values on the left and right. So here, what I'm asking is, give me a Boolean index where I have values that are greater than 5 and also less than 9. So values that are within that range, 6, 7, or 8. And I get true for all of the values in the array that fall within that range, 6, 7, or 8. Now I've wiped out my array here, so let me go back and recreate my array. Fortunately, I can just copy and paste this whole thing. Alright, so here's my original A1 again, and I can say things like A1 is greater than 3. I need to use parentheses for precedence reasons. A1 is greater than 3, and A1 mod 2 equals 0. All right, so what I'm doing here is I'm saying identify for me all of the values in A1 that are greater than 3 and even. Actually, I made a mistake there. I better say is equal to, not gets. Okay, so values that are greater than 3 and even. Let's see what we get. Actually, just these 3 in the top row. So these are the only values in the array that are both greater than 3 and even. All right, and so now I can select those out and trim them or change them or whatever I want to do. Make sense? I'm seeing a lot of glazed eyes this late in the course. Well, I'll try to get done in 4 minutes. That's what we got left here. All right, so that was Boolean indexes, where you can select out components or items within an ND array by their characteristics rather than by their location, their physical location in the array. So we got slices for physical location, we've got Boolean for characteristics. We can also do what's called fancy indexing, and here I think the person who developed NDArray, the person who developed Numpy, just couldn't think of anything good to call this kind of indexing, so he shrugged and said, "Oh, this is fancy. We'll call it fancy." We're really just using integer indexes to select out certain subparts of an array. All right, so I've got my array A1, and fancy indexing involves using a list of row or column numbers either in the row position or the column position when you do your selection. All right, what the heck did he just say? Well, let's take a look. So A1 is this entire array, and if I say A1 sub 2:4, that's a slice, right? It means row sub 2, row sub 3, but not row sub 4. So I've got a slice of 2 rows. Using fancy indexing, I can say 2, 4 in square brackets, which means give me row sub 2 and row sub 4. Of course, I just realized there's a problem here because there is no row sub 4. So let me choose row sub 1 instead. All right, so now I'm going to get from A1 row sub 2, okay, the third row, followed by row sub 1. So not only does this allow me to select certain rows, but it also allows me to change the order of those rows using the so-called fancy indexing. And in fact, I can also repeat rows. So I can say, give me row 0, 0, 0, 0, 0. This gives me an array consisting of 5 rows that are all copies of row 0. Now, if I want to do fancy indexing on columns, I need to use the slice notation to specify all the rows, and then I can use, what did I do there? I made some mistake. What did I do? All right, so A1 sub colon comma. So I'm getting all the rows now because I've used the colon slice for my rows, and now my fancy indexes on my columns, I can say, give me column 4, column 2, column 0, and then another copy of 2 and another copy of 4. Okay, and so I've got a copy of row sub 4, row sub 2, row sub 0, and then another copy of 2 and another copy of 4. All right, so by combining slices and Boolean indexes and fancy indexes, you really have hugely flexible control over how you deal with the subsets of data that you select and the reorganization of that data into a different form of array once you've decided what data you want to work with. Okay? Are we done? Oh, almost. Almost. Okay. I'm going to skip slide 65 and let you do that yourself. So we have looked at how to create ND arrays and characteristics of ND arrays, namely that they have to contain data that is all of the same data type, unlike lists, and you do vector-oriented operations on them rather than item-oriented operations. We then looked at different ways of selecting and munging data contained within ND arrays. Above and beyond this, there is a whole collection of mathematical functions, statistical functions, random number functions, linear algebra functions, sorting and subsetting functions. There's all kinds of additional functions available in NumPy for analyzing all of this data once you have decided which data you want and how you want the data organized. And those functions are actually pretty straightforward. I mean, square root means square root, and exp means e to the x, and mean and sum and standard deviation mean what they sound like they mean. Any questions? Rats, it's 1 minute past time. Any questions? Okay, so again, I apologize for being absent last week. If you do have questions for me about the material or about the homework, I will be here tomorrow at least by 11. I'll try to get here earlier than that. And I'll try to stay fairly late. I'll be here until at least 5. So 11 to 5, I'll be here all day. I'll be here tomorrow for sure. And I'll try to be here earlier and stay later. And then on Thursday, I'm also going to try to be here fairly early and stay fairly late. So I'll be up in my office if I can be of any help at all. Okay? Alrighty. Well, good to see you all again.